Hello, my name is Gong Chen from the university, and I'm very happy to present our paper Generating Compact and Relaxable Answers to Keyword Queries over Knowledge Graphs. This is a joint work with Shu Xing and Ke from the university, and also with Chen Kai from University of Texas at Arlington. So we are familiar with keyword search, and here we show a knowledge graph. It describes some countries, some cities, some broadcast companies, and some series, um, and also some parks, some groups or organizations. Um, so the keyword query, it aims to find some trips to park in the United States. How can we answer this keyword query with this knowledge graph? There have been two types of methods. The first type of method is to transform a keyword query into a Sparkle query or other formal query. And this is called semantic parsing. Semantic parsing is particularly suitable for lookup tasks where there is a precise information need that can be precisely expressed as a formal query. But in this work, we consider the other case, the other type of methods. It is called answer subgraph extraction. The idea is that we directly extract the subgraphs that can cover all the query keywords as an answer to the query. And this kind of method is particularly suitable for exploratory tasks, while the information need is kind of weak and not clear, so that we may not be able to transform it into a precise Sparkle query. So we just extract some top-ranked subgraphs. And it has been standard in the literature to use group standard tree as the answer subgraph to find. A group standard tree, or GST, is a minimum weight subgraph that connects all the keywords in the query. For example, in this case, you can see this path from YSMP to TT. This path is very long, but it covers all the 5 keywords in the query. So it is a GST that we may return as an answer. This is a kind of a standard solution, but GST has both strength and weakness. The strength is that GST is a complete answer because it covers all the query keywords. The weakness is that GST is not a compact answer. It may not have a compact structure that is favored by human users. For example, in this case, this GST is a very long path. Its diameter or its length is actually 7, which is quite long, quite large, not good for human users. So our focus in this work is that whether we can achieve a better trade-off between answer completeness and answer compactness. We do find a way to better trade off between these two factors. We want to compute compact but relaxable subgraphs as answers to keyword queries. Our idea is that we want to guarantee answer compactness. We want to define a bound for the diameter of an allowable answer. The bound is called D, so that we can have a guaranteed answer compactness. But in the meantime, because the diameter of an answer subgraph has been bounded, it is possible that there is no answer subgraph that can connect all the keywords in a query. This is possible. So our solution is that in the meantime, we do not require an answer subgraph to cover all the query keywords. Instead, we only aim at maximizing answer completeness. We want to cover as many query keywords as possible. So still for this example, instead of showing this GST, we choose to only return this very short path as an answer. This subgraph, the diameter is only 2, right? So suppose that the diameter bound is set to 2, so we can only find a subgraph having a diameter of at most 2. So this subgraph satisfies these requirements. However, in order to satisfy this compactness requirement, we can't, and it is impossible to cover all the 5 query keywords. And for this case, we can cover 4 keywords. It's not bad, right? We can cover 4 out of the 5 keywords in the query. So 1 keyword can't be covered, but we have a very high compactness. So this is the trade-off that we want to achieve in this work. How we do that? How can we find such answers, such compact and relaxable answers very efficiently? So our algorithm is based on the following proposition. I don't want to go to the details of this proposition because it's very complex, but the idea is that we actually establish a necessary and sufficient condition for the existence of a compactness bounded complete answer to a keyword query. The idea is that, for example, suppose we have a query containing 4 keywords: United States, Yellowstone Park, and we are given a diameter bound of d equal to 2. Is there any answer that satisfies this diameter bound and also cover all these 4 keywords? The answer is yes. We know this answer not because we actually search for such a sum, but because we only need to compute a few distances according to this proposition. The key concept here is a certificate vertex we define here. So in this case, Montana, this vertex is a certificate vertex for this query because we can show that Montana is very close to all 4 keywords. So based on their distances, we can, and using this proposition, we know that, okay, we find this special vertex, this certificate vertex, and this vertex is close, is fairly close to all the keywords in the query, so we can immediately decide that, okay, such an answer exists, and then we can easily construct such an answer based on the computed distances. So with this proposition, now we introduce our algorithm. The algorithm is called CORE. CORE is the best first search algorithm. So the idea is that we perform one independent search starting from each keyword vertex. Suppose that we have 5 keywords, and each keyword is mapped to 10 vertices in the graph. Then we have 50 unique keyword vertices that are mapped from keywords in the query. Then we will run 50 independent searches. But all these searches, okay, so all these searches, they maintain their own list of visited vertices, but all these searches, they share a priority queue to keep their search frontiers. We use a mean priority queue. So the smaller the priority, the better the vertex. We define the priority of a vertex as the number of potentially uncovered keywords. And this number is computed based on distances according to the proposition that we have just introduced. So I will just ignore the details here, but the idea is that we do best first search. So because it's best first search, so we do many iterations, and in each iteration, we will check the top ranked vertex in the priority queue, I mean the main priority vertex. So if a more complete answer, which this current vertex is a certificate vertex for, can be found, we will update the current best answer. And then we will explore the unvisited neighbors. Then we just iterating this way, but in many cases, we don't really need to explore every vertex in the graph because we can stop early. Here is the stop criteria. If the priority of the main priority vertex is larger, or I mean is worse, then the current best answer, we can stop. Why? Because if the number of potentially uncovered keywords of the unseen answers is is at least as large as the number of keywords that are not covered by the current best answer, then we know that better answers do not exist, so we can stop early. Very straightforward idea. So I can show you with this round example. We start with 5 keywords, and each keyword is mapped to 1 or 2 keyword vertices. So we have 5 unique keyword vertices, and we have to run 5 independent searches. And initially, the priority queue contains 5 vertices to be explored, and we compute their priorities. So YSMP is the top ranked one, and it is popped out of the priority queue, and it is checked. And we find an answer which is not good, which only contains this single node itself. So it misses 3 keywords in the query. Then we continue to explore its neighbor Montana, and by computing distances from Montana to the keyword vertices, we know that okay, with Montana as a certificate vertex, we can find an answer that contains 4 out of the 5 keywords. Then we find this answer very easily. So we update the current best answer. So now only 1 keyword is not covered, and in the meantime, we find that the main priority vertex, the main priority in the queue is also 1. That is, if we continue to search, we can't find a better answer, so we can stop very easily, very early. We only explore a small portion of the knowledge graph, then we stop. So it's a very efficient algorithm. So we did some experiments based on 3 popular knowledge graphs, including DBpedia. We compared with an existing baseline algorithm that can be adapted to our problem, and we also compared with GST-based answers, the traditional answers. We show that okay, traditional answers do not work because the GSTs in practice can have a very large structure. Their diameters can be as large as 8 or even 10, so it's not good for human users to read. So we need to trade off answer completeness for compactness. Well, in the meantime, even though we allow relaxable answers, the completeness of our completed answer is very high in practice. In normal settings, relaxation is not needed. It does not happen in practice, but when it has to happen, when we have to drop some keywords, we usually only need to drop 1 keyword. Very occasionally, we have to drop 2 keywords. That is the case, so the completeness is reasonably good. We also compare with baselines, and the results show that our algorithms is very fast, much faster than the baselines. For example, on DBpedia, we use only 4 or 6 seconds to process a query on average. Our code is open source, and please feel free to try it. Thank you for your attention.